Good morning, everybody. Thanks for having me here. My name is Joachim Sachs, and I will be talking for the Deterministic 6G project on 6G for dependable communication. I will have some more general reflections on 6G before diving into these dependable time-critical communication. And then when we think of the 6G architecture, then we see general trends that will be, let's say, the foundation for how the 6G architecture will develop. And that will be that it will be an architecture that is AI-enabled and allows for data-driven operation. We see also the trend of cloudification, virtualization, and distributed compute, and the need for being able to provide more or flexible topologies. We also see that we go support edge computing, allowing offloading of computing from the device domain. And then, and we've heard this in the presentation before, automation is an important topic for the operation of a 6G network, allowing also then optimization, and the general trend for automation is to make it intent-based. And then there's exposure, which allows for the interactions from the network to the application domain. And a lot of focus will be on key value indicators and support for sustainability. Another aspect that is quite important is how to enable an efficient migration to 6G. So what we foresee from a high-level architecture, and now there's a reference here, this is now an Ericsson view on high-level architecture, is that we will have a horizontal architecture with different horizontal layers, where it is important that we identify what are the key interfaces that need to be supported, and in particular, which of those need to be standardized. And of course, all the focus should be on very important it is to standardize those interfaces which are important for multi-vendor integration. So we see on the top here the management and orchestration layer, which allows also to make the services of the network monetizable, which means providing the value to the applications that is needed. We have the access, mobility, and network applications layer, which is based on an infrastructure layer, which enables cloud-based realizations, and we will have a data pipeline for data collection, and we have, of course, a transport that interconnects the different network domains. I don't go further into the details of this now, as there are later questions on that. And now I will say something about the architecture evolution. If we think of where we are with 5G today, we have seen the migration from 3G to 4G to 5G. And in the step of 5G, we see actually that there's a step in between, which is 5G non-standalone, and where most of the market is today, which is then on the way for going to a 5G SA deployment. And then we see the services that were supported. So in 3G, we had circuit switch and packet switch services. With 4G, we moved to mobile broadband, voice over LTE, and massive machine type communications, which continued then into this 5G NSA solutions, which still use very much the 4G infrastructure as a baseline. And a lot of the new services that were specified for 5G become available from the moment that we transition to a 5G standalone deployment. When we think of these migrations and take the learnings that we see from 4G to 5G, there were quite many different multi-connectivity options supported, depending on if the 4G RAN or the 5G RAN was used, or if the 4G core network or the 5G core network was used. And this resulted in then 7 migration options, which some of them had even sub-variants. And quite a number of those have been standardized, which put a significant amount of effort into the standardization. And it also created a fragmentation of the market. And so of today, I don't think 5G is really yet living up to its full standard potential. So if we look into the latest market analysis where we stand today, we have 1.6 billion 5G subscribers. 20% of the operator 5G networks are 5G standalone, based on a 5G standalone architecture. The rest is non-standalone. And by now, 90% of the devices support 5G standalone. I think what is important here to consider is that I think it's important from the adoption and deployment of 6G to achieve an industry alignment at an early stage, which means not going through standardizing a lot of different options, of which many will not make it to the market, but try to have as much as possible an alignment in the industry and the ecosystem of finding the valuable options that are really the ones that are most relevant for the market. What we see as the migration towards 6G, we would like to see that standalone 6G is the preferred way to introduce 6G, which means that we will have a direct connection from the 6G device through the 6G radio access network to a core network. Then we see that a lot of the investments in the core network are still going on the deployment of the 5G core as part of this transition towards 5G SA. And this will continue during the entire 2020s, which means pretty much in the time frame that is preparing us now for then introducing 6G. And it provides a flexible network platform enabling service innovation. And we see and propose that the 5G core should be evolved to provide the core network functionality towards the 6G RAN to enable an efficient transition. And that means that from a deployment of our coexistence of 5G and 6G, we see that the solutions that we should have standalone kind of approaches, which means 5G devices connect via the 5G RAN to the core network, 6G devices via the 6G RAN, and coexistence is achieved by means of allowing 5G and 6G to share a common spectrum, and that is enabled via multi-radio spectrum sharing. So that is, at least from Ericsson's side, the proposal to move into the 6G timeframe. And now I want to go into a little bit this dependable communications that we address in deterministic 6G. So in deterministic 6G, we look into an end-to-end deterministic system architecture where we want to look into 6G use cases which require deterministic communications and have corresponding service requirements. And then we investigate in this project approaches for being efficient in providing these end-to-end communications, dependable communications for time-critical services. So the time-critical applications, we see that there's still an increasing number of time-critical applications. In an example that is often given is industrial automations, but this is also the case when we go to XR communications or connecting the smart grid and many others. And what is a common requirement is that we have requirements on a guaranteed bounded latency, which has to be provided with a high availability, which means the guarantee of being able to meet these requirements. Some of the use cases that we explicitly look into in the deterministic 6G project is connecting occupational exoskeletons, looking into extended reality, looking into flexible productions or the manufacturing area control applications in flexible production, as well as smart farming. And when you step a little bit back, then often these kind of time-critical applications come when we look into this transition into this cyber-physical world, where we have parts of the physical world connected to a digital representation or digital twin in the digital world. And a lot of the time-critical applications come when we have monitoring or control of the physical elements from their digital representations, where we see these requirements appearing. And in several of these use cases that we investigate, offloading is an important part where the compute is moved from these physical assets into an edge cloud and is executed there. And then they become part of the physical world operations because we have this closed loop, which is between the physical world and the digital representation, which has part of the monitoring and control. Examples for this is when we put spatial compute from XR, from offloading these classes to execute the computing for spatial compute in the edge cloud, or when we have some control applications that are collaboration friendly, where you want to coordinate different entities from a common control logic, or you want to introduce machine learning based approaches into the control. But also a reason can be device simplicity, that by offloading functionality from the device, you can have lower power consumptions on the device, a smaller footprint, and reduced complexity, which can be also a strong driving force in this direction. And this is, for example, one very important part in our use cases for both the exoskeleton as well as for the XR use case, for providing the capabilities of having lighter and simpler end devices. Then what is important for this time-critical communication, we need some time awareness. If you are time-critical, it means you are time-bounded, which means your elements need a notion of time. And time awareness, and good foundations for this is the time synchronization functionality that has been introduced and which will be in releases 16 to 18. And end-to-end, this communication is very often based on some time-sensitive networking technologies, which are in particular, when in the Ethernet world, IEEE time-sensitive networking as a kind of a time-sensitive or a time-critical communication extensions to the Ethernet standard. And in the IP world, there's deterministic networking as an add-on to IP networks for providing more deterministic in time-critical communication. When we talk about dependable time-critical communications, then how we define dependable communication is that we must be able to quantitatively ascertain that the delivery of a required service performance for the communications as it was agreed in the service contract. And that means if we break this down, what does this really put as requirement in? Then we see that there are several steps which are being applied. First, we need a clarity on the required and agreed service performance, because that's what we have to deliver on. Then we must be able to monitor and predict what the service is that we are actually delivering. And that is then an input that can be used for automated service assurance, but also we need to be able to provide feedback to the application domain on the service quality that has been delivered. And in that way, we are working on this enabler for allowing some application communication co-design, as I will show a bit later. So if I break this down now a little bit, so we need in the exposure layer the capabilities for having a good specification and configuration of time-critical services, which means we must be able to know what the traffic characteristics are that need to be supported and what the latency bounds and reliability requirements on this traffic is. Then we need mechanisms for making the performance that we see in the network observable, so that we know what latency we can deliver to the services. And also what we work on a lot in Deterministic 6G is to be able to take this and from being able to make predictions on the performance that can be provided. And that means we must have a way, a framework for collecting this data on the service performance and apply machine learning based prediction on this data that is collected for being able to see if we can still maintain for the upcoming time the required service performance, or if we deviate from this and need to take corrective actions. For the service assurance, it's important that we know the service specifications, but also the preferences of the applications, which means that we can use this in management. And there we see that a corresponding information from the application is needed. And most likely this should be expressed in an intent-based fashion. And what is also then required for the services is to be able to get the feedback on the service delivery that has been provided on the quality. And here we come also into the area we hear often about this communication control compute co-design, or more generalized some kind of application or network aware applications or application communication co-design. I think it's important that we enable this information exchange, that as an enabler, as a tool for this kind of smarter applications that can make more effective use of wireless communication. Then, as I said, on the end-to-end perspective, a lot of these servers are going to use either time-sensitive networking or deterministic networking, which means an interworking with these end-to-end communication frameworks is needed. And so this is what we see are the main tools that are used in the industry in this direction. And sometimes there's some kind of application middleware in between to help in the configuration of this, for example, TSN configurations. And one of these middleware frameworks used in the industry is OPC-UA for field level communication. We should be able to interwork with these functionality. And then, of course, 5G has already provided foundations for interworking with TSN and DetNet in releases 16 to 18. And this then is a good baseline for improving on our way for 6G. So what we also see is, or investigate in our project, is how we can make this interaction from the 5G or 6G network domain towards this control side of the TSN or DetNet side, how we can improve this to make this end-to-end communications over 6G work better. And with this, I'm at the end of my presentations, and I want to say that we have just released a number of deliverables. So one which is on the use cases and the architecture principles. Then one which is on the 6G-centric enablers, where we see how can we make 6G add some functionality there, for example, for latency prediction, but also for more deterministic latency behavior. And we have looked into time synchronization, improving the time synchronizations, but also how this convergence of the TSN and DetNet domain with the 5G, 6G domain can be improved. We have also developed a simulator framework that has been released. And so on this website, you find all these deliverables available where you can find more information. And with this, I'm at the end of what I plan to say here.
Okay, thank you very much. There is a question that in some use case, there is no strict KPI, high bandwidth, low delay, high reliability, and usually only 2 out of 3 is needed. And it was asked if you will provide more detail. And another question is also related to the timer synchronization accuracy for the different mentioned applications.
So we have started to look with our industrial partners into some use cases. I think what is important that we get a proper information about what service performance needs to be delivered. And if the network can only do its best according to what it knows that it should be doing. So it's very important that we get the right information. So if a service is not properly defining its requirements, then it's very hard for the network to deliver on that. So that is one of the activities that we are starting up. A report will become later during this year, where we will explicitly provide or want to investigate what is the right level of information that should be exchanged between the applications and the network, and in what form should this be specified. Our assumptions is that we simply get, for example, if you have latency bounds, you need to, and you should get this information. Something which is in many of these control applications a little bit more implicit. Data rate is something which comes, often you have a rather constant periodic communication patterns, which means data rate is something where you don't have very demanding data rate requirements, but they come from the way on how the application is designed, and they are implicit by the traffic profile that comes. And of course, then you need to provide this, but the main requirement is then on the delay of these individual messages. So I'm not sure if I answered the question here properly, but this is how we see it. Of course, we can only deliver on the service requirements that have been expressed to the network.
I think it's fine. I think we need. I was more about the usual definition of KPIs, but that we can discuss a bit further, because I think that we just started some discussions with ITU people. I think also with some of your project members like János, Balázs. So I think we can discuss it further, because it's an important topic. For us, it's important because we have to understand what is that we are building in the desired 6G project, at least, that I will also present anyway. It's an important input.
And maybe to add on, so what we have not seen is the requirement types that we see are not different from what we have seen in the 5G definitions, where we also had many of these control applications were already addressed and taken up in SA1 and 3GPP in 22104, for example. And it's the same kind of requirements, which is a latency bound and a reliability or a communication service availability requirement. So there we have not seen something that significantly deviates from this. The question is, how can we work in this domain better between the network and the application domain? That is a little bit the area we focus on, where we want to explore how the service interface can be maybe improved. And then there was a second question, which was something on time synchronization. The requirements on time synchronization, we have not seen anything that goes beyond that of what was also put into the requirements for 5G in 22104. Which means for the industrial profile of TSN, it's required to enable end-to-end time synchronization with 1 microsecond maximum timing error, and that should work over multiple hops, which means that 5G or 6G is going to be one part of this end-to-end communication chain. Then we have a fraction on this. I think in 3GPP it was put as a requirement on 5G to be 900 nanoseconds. We have not seen any use case which has tougher requirements than that. What is a bit of a question is how sensitive is the timing information? Should there be resilience inbuilt into time distribution? Since if we are time aware and operate very much on a time basis, if that becomes an area of sensitivity, if it becomes erroneous or manipulated. So that is something that we look into right now. And for example, for the industrial profile of TSN, some resiliency to the time distribution is being worked on.